All right, we'll be talking about some of the stuff we can learn from our CAV lab. So first up, we'll just take a look at each of the graphs. So this is a car that is moving downhill, so it's speeding up and going to the right. Take a look at our position time graph here. It's curved and it gets steeper as time goes on. Our velocity graph, pay close attention to the values here, so positive, negative. Some of these look pretty similar. So this one, positive values, getting more positive. If we look next at an object, so the car is going downhill, so speeding up, this time to the left. Notice again, it gets steeper as time goes on, but this time it's going the opposite direction. Here we have negative values for velocity that get more negative. If we look at this next one, this is going uphill, so it's slowing down to the right. So this time it starts steep and it gets flatter, but still going in the positive direction or going up on our graph. And then our velocity, positive values that get smaller as time goes on. Last combo we can have is going uphill, so it's slowing down to the left. This time it starts steep, gets flatter as time goes on, start with positive numbers, going into negative numbers at the end. This time we have negative velocities that get closer to zero as time goes on. So let's take a look and recap what we know of y-intercepts. So on a position time graph, the y-intercept still represents the initial position, so that doesn't change from last unit. If we take a look at our setup here, if we look, our car is over here to the left of the origin. In fact, it's 1.2 meters to the left of the origin. So take a look at our position time graph. It still shows up at negative 1.2 meters for our y-intercept. So even though the graph is curved now, nothing changes from last unit with y-intercept. It still represents the initial position. If instead the car started over here to the right of the origin, we just start with some positive y-intercept instead. If we look at the slope of the position time graph, it still represents the velocity. This time it just is a little different because our line is curved. So we have to do something called draw a tangent line. You've heard that word in math class before. It just means draw a line that only touches the curve once. So it doesn't like intersect it at multiple spots. It just touches it once. So here's what that tangent line looks like at the start. It is a pretty flat slope and it's positive. So that means, remember last unit, it starts out with a flat slope. That means it's moving slowly, and positive means it's moving to the right. If we look at the end here, now our slope is steeper and it's still positive. So steeper means it's moving faster, still positive means it's still moving to the right. So in this graph, our object starts out slow because we have a flat slope, and the slope generally gets steeper as time goes on. So that means that it's getting faster. Since this slope is positive and this slope is positive, and any spot on here, if you were to draw this tangent line and look at the slope, it would be positive. It's moving to the right the whole time. And this was, in fact, the car that sped up to the right. Now, if we look at our new graph, here's our velocity time graph. So the y-intercept on a velocity time graph, it just represents the initial velocity. So think of the parallels to the position time graph. The y-intercept there just represented the initial position. Now on a velocity time graph, it represents the initial velocity. If we go back to our video, so here, this is a car that starts slow or starts at rest and speeds up as time goes on. So it's starting out slowly, which is why if we look at our y-intercept on our velocity time graph here, it's close to zero. So it's like 0.29, 0.3, somewhere in that range. So it's pretty close to zero. In fact, it should be exactly zero. That difference is just some error in our measurements. If now we look at the slope of a velocity time graph, this is a new thing called the acceleration. It just represents the change in velocity each second. So if we think back to position time graphs, the slope there was velocity, and that just told you how much does the position change every second. Now, the velocity time graph, its slope represents the acceleration, and that is simply telling you how much does it change its velocity each second. So if we look at this one, first up, it's important again to look at our axes here to notice these are positive values, so we have a positive value for velocity. The slope isn't zero, so that tells us we have a changing velocity. It is also a constant slope since we have a linear graph, so that means there's a constant and predictable change in speed. And our slope here is positive, so this object is increasing speed. Now let's take a look at an object that has negative velocities. So if we look over here, notice these are negative velocities. Remember from last unit, this is still true. A negative velocity just means it's moving to the left. So this one, now let's look at the slope. The slope isn't 0, so we know it's changing its velocity. It is constant, so we know there is a constant change in speed. And this time, the slope is positive, but it's decreasing speed. So look at this one. The difference here is that we have a negative velocity with a positive slope. And that might be a little confusing to think about. So instead, just look at these values. My velocity here starts out at like negative 1.2, so it's moving left at 1.2 meters per second. And then at the end, it's pretty close to 0. So now its velocity is like 0. And we know if something's velocity goes from like 1 to 0, it's slowing down. So don't think too much about like positive, negative slope. Try and remember these values. The values will help you know if it's speeding up or slowing down. If we look, there are 4 different possibilities here. So this is probably the easiest one. This is an object that starts with a velocity of 0 and speeds up or gets a bigger velocity as time goes on. So in this example, we have a positive velocity because all of these numbers, like if I pick a number right here, let's say that's a velocity of 2, and then I pick a number up here, that's a velocity of like 4. So those are positive values that are increasing, so positive velocities with positive slopes. That means it is speeding up to the right. If instead I look at this graph, so now my velocity, let's say it starts at 5 and ends at 0, starts at positive 5 and ends at 0. So this object is moving to the right at 5 meters per second if we just make up a number here, and then at the end it's 0. So we know that's slowing down and moving to the right. So when we have a positive velocity with a negative slope, it's moving to the right but slowing down. Now if we look at this object, it has a negative velocity that gets closer to 0. So this negative velocity here tells us it's moving left. Getting closer to 0 means it's slowing down. So when we put a negative velocity with a positive slope, this is now slowing down, going to the left. And the last combination we can have is an object that starts at rest, so starts with 0 velocity, and ends with a big negative velocity, so this object is speeding up to the left. When we have a negative velocity with a negative slope, it's speeding up to the left. So since there's 4 different combinations, this is a helpful way to kind of organize them all, because it doesn't always just happen to be that a positive slope means an object is speeding up. That's probably the biggest mistake students make. So you need to look at the sign, really. So a positive velocity, that tells you that the object is moving to the right. So if you look at this, this is moving to the right, this is moving to the right. Then we need to look at the sign. So positive with positive means it's speeding up. If I have a negative velocity with a negative velocity, it's also speeding up. But when there's a mismatch, so if I have a positive velocity with a negative acceleration, that would be slowing down. And if I have a negative velocity with a positive acceleration, that is also slowing down. So when we look at this, we use the sign on velocity to tell us, is it going to the right? So positive to the right, or to the left. Negative velocities still mean moving left, so that hasn't changed from last unit. And don't look at the sign of acceleration. That's not super helpful. You just need to look at whether or not it matches. So if it's positive velocity with a positive acceleration, it's speeding up. Positive with negative, then it's slowing down. And the same goes if we have a negative velocity. So to recap, the same things that are still true from last unit, y-intercept of a position time graph is still the starting position. The slope of a position time graph is still the velocity. This time it just might be a changing slope as time goes on, so we'll see curved lines. When we have positive slopes, when we have positive y-intercepts, that means the object's moving to the right. When they're negative, that means it's left. So that is still all true. Here's the new stuff from this lab. We can have position time graphs that are curved. That happens when an object is changing its speed. When the line is getting steeper, so when it gets steeper as time goes on, the slope gets bigger and bigger, that is speeding up. When it is flattening, so getting less steep, that's when it's slowing down. On a velocity time graph, the y-intercept is just the starting velocity. Again, notice this parallel here. Y-intercept of position time is just starting position. Y-intercept of velocity time is just starting velocity. And then the slope of the velocity time graph is the acceleration. And that's just the vocabulary word now for change in velocity per second. We call that acceleration, just like we called change in position per second the velocity. In terms of our graph, so on your velocity time graph, it was just linear. So we know that fits just y equals mx plus b, but we don't want to use y equals mx plus b in physics class. We want to use the actual variables that we have. So instead of y, we're now calling it velocity. So in this case, we're saying final velocity equals our slope, which is the acceleration, times the change in time. This is like x in our y equals mx plus b, and then plus our y-intercept, which is initial velocity. So once again, acceleration, that is just our slope of the graph. So in this case, like if I look at my values here, my acceleration of this car would be 0.7468 meters per second squared, or in our case, centimeters per second squared. And then the initial velocity, that's just the y-intercept. So this one starts, we'll say it's like 0.3. So our initial velocity of this object is like 0.3. As you write your CER statement at the end, we're just going to go through each of the parts. So the expectations for the claim, you want to answer the question, what is the relationship between velocity and time for the car as it moves on a ramp? So basically you can use this flowchart. Does the car change its velocity? If the answer is no, that means there's no relationship. So as time goes on, if the velocity never changes, then there's just not a relationship. If it does change, then we need to ask ourselves, is the change constant? So do we see a linear graph? And this is true for any lab besides just this one. So if we see a constant change, we call that directly proportional. If we see and this is a little confusing, if we see a change that is changing, so if we see a non-constant change, so like if between values, the first set of values, it goes up by 10, and then the next set of equally spaced values, it goes up by 20, that would be a changing change. We call that quadratic or sinusoidal or whatever. So we would say that relationship is, and we just use the term, it's quadratic. You've seen this in math class before, sinusoidal, so that's just like a line that goes up and down. So this is what we need for the claim. For the evidence, you want to talk about your velocity time graph here. So remember, in the claim, you're saying, what is that relationship? And now you want to say, well, here's my evidence for that relationship. So talk about the shape of the graph. And then we want to say, what does the slope represent on your velocity time graph? What was your value for that slope? What does the y-intercept represent? What was your value for that y-intercept? And lastly, we'll talk about, or last section is reasoning. In the reasoning, we basically just want you to say, what is the new physics from this lab? So I just talked through all of it, so you can go back and you're basically restating things from this video. So in general, we want to say, is there a generalized version of your equation that can be used for other objects? Because as fun as it was to look at the video of the car as it's changing speeds, we want to know, can we use this on other objects that aren't just a car going down a ramp on our video? So is there a generalized equation that you can use? And if so, when can and can't you use this equation? So like, what are its limitations? So you can go back, watch parts of this video. This video is basically what you're using for the reasoning.